Hey y'all, we are Memphis Community University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today we're going to be doing the advanced derivative topic of optimization. So keep in mind that optimization isn't the biggest topic on the AP exam. It appears a lot less frequently than, for example, related rates, but optimization does appear a lot on college calculus exams, and it's still useful for people that are taking the AP exam because as we talk about this optimization lesson, we're really going to be talking about another lesson as well, a review of a lesson, which is trying to find the alternative way to do absolute max or min. So instead of having that closed interval method where we do locate the function, take the derivative, find some zeros, and then plug it into a table, what we're going to do is we're going to instead do the alternative way to do absolute max or min. So if you need a refresher on that, this is the video for you. So again, a nice little two lessons in one. So let's get started. So like normal, optimization does include some steps. So let's list out those steps. So the first step basically will be, sometimes you're going to have what is called the constraint function, and you're going to try to find the maximum or minimum of another function. And this other function unfortunately has multiple variables, so you won't know what to do with them. But what we're going to do is you're going to use the constraint function to turn the function you care about in terms of just one variable using some sort of substitution process. So the first step will be change function, the thing you're taking the maximum of, into one variable. Let's call this function f of x. So I'm trying to maximize or minimize f of x, and we're going to change that into terms of one variable using what is another equation. So this is called the constraint. So again, you're going to usually have two functions, the constraint and the thing you care about. The constraint, the only use of the constraint is to change the thing you care about into a simpler thing. So you're just going to plug it in. You'll see this. So the second step will be, of course, take the derivative. This is an advanced derivative topic where the main step in most of the questions is take a derivative. So we're going to take a derivative. And what we're going to do is after we take the derivative, we're going to draw a sign chart of this derivative. The derivative sign chart is going to have to be easy enough where we can apply the alternative way to do absolute max or min. Another way to say this is the first derivative test for absolute extrema. So that's going to be the next sort of thing I write on the board after we write out these steps. So it's going to be a nice little sign chart. And then what you're going to do is you're going to apply the abs max, the first derivative test. So first derivative test for abs max or min. Again, this is used to justify that whatever zero you get in step 2 is your max or min. That's where it occurs. And you have to write a nice little sentence. I'll write the sentences after this. And that's going to justify that you have the max or min. Finally, in step 4, find what you need by plugging in. So find the answers by plugging in. You might need to find where the maximum occurs. You might need to find the other variable from the constraint formula. And you might need to find the actual max or min value by plugging in the f of x. So find answers by plugging in. So it's not going to be too hard of a process. Again, all we're going to do is change one function to be in terms of one variable using another function. Then we're going to take a nice derivative, draw a sign chart, and then we're going to write a sentence using the first derivative test for absolute extrema. And then we're going to finish it off by plugging in stuff. So these are the optimization steps. Write these down if you want. But again, this is a 2-lesson sort of video. So I want to talk about the alternative way to do absolute max or min after this. So take this guy, sort of absorb it, and then let me erase this then. So again, we're going to talk about one thing before we talk about and do some questions. So the next thing I'm going to talk about is the alternative way, or the first derivative test for absolute extrema. And again, even if these questions are not optimization, you employ this when you don't know how to do the closed interval method. So the closed interval method should be your first instinct anytime you're doing absolute max or min. Take that nice function, you take a derivative, set it equal to 0, that's the critical point step. Finally, in step 3, you draw a nice little table, plug in your critical points into that table, into your locate function. But sometimes they don't give you a closed interval for closed interval as a given. So then you can't do the closed interval method, as the name implies. So you have to be forced to do this. So this does occur in outside of optimization questions. So what happens is that the sign chart is going to be very, very easy. The sign chart is either going to be something like at A that goes from negative to positive, or the sign chart is going to be from positive to negative. And again, we have covered this in our absolute max or min video, but I do want to repeat it. Hopefully this makes sense. If you're going from negative to positive and that's all you do, that means that your derivative is negative, means your slope is going down. Your slope is negative, sorry, so you're going down. If your derivative is positive, that means your slope is positive, so you're going up. So if this is your sign chart, that means that all you did was you ran downhill and then you ran uphill. So at this point, it has to be a valley, and it has to be the only valley, really. Same thing with the max. If you're running uphill and then you run downhill, the only thing you did was run over a hill. So notice that we're not talking about local max or min, like every single max or min that are possible, every single hill or valley. We're only talking about the extreme one and the extreme one. And if this is your sort of your sign chart, it only does one thing basically. You only have one valley or you only have one hill. So that hill has to be the absolute max because you only have one of them. Same thing with the minimum, it has to be the minimum. So what you do when you justify this, unfortunately sign charts don't give you points on an AP exam, for example. You have to justify it with a nice justification sentence. So this is the justification sentence. F has an abs min. So this is the absolute min picture. Hopefully you can tell, negative to positive. At this number, x is equal to a, because f prime goes from negative for x smaller than a. So it's actually slightly different than the local min sentence. The local min sentence is f prime goes from negative to positive, but you only care about that at that one point. Here I'm trying to describe the entire sign chart, so I'm including an entire interval. F prime is negative for x smaller than a. And then what it does is f prime is bigger for x bigger than a. Some of my students memorize this, but I don't think it's necessary. You're just describing the sign chart as precisely as possible. It's negative for this half of the sign chart, it's positive for this side of the sign chart, so it has to be an absolute min. The absolute max sentence is really similar, except a few things are reversed. So abs max at x is equal to a, because f prime is positive for x smaller than the number, and then f prime is negative for x bigger than the number. So again, this is going to be sort of the latter stages when we do these optimization questions, because we're going to locate a function, we're going to plug in some variables to make it one variable, we're going to take the derivative sign chart has to be this easy, and then once we justify that it's an absolute max or min, we are good to go. So this is the second half, or the second part of this two-part lesson. Let's actually do some examples. So I'm going to erase this and let's go for our first example. So my first question is, if y is equal to, let's see, 2x plus 1, yes, then find the minimum, the absolute minimum of course, of f of x is equal to x squared plus 2y. So this is my first question. So notice again, we have two sort of functions here. We have what is called the constraint. The constraint is what you know. So in this case, we know that y is equal to 2x plus 1. The thing you're taking the absolute max or min of is the other function. So in this case, the function that matters is this f of x, and we're going to use the y in order to sort of manipulate this. So notice that I like to write out what I'm trying to find the max or min of. In this case, it's just the min. So it's f of x is equal to x squared plus 2y. We look at this function and we start panicking because we have two variables and we don't know how to take derivatives of two variables. But again, you use this lovely constraint function to take this and plug it in so that it's only of one variable. So in this case, it's going to be x squared plus 2 instead of y. Well, I know what y is. It's 2x plus 1. And notice that when I write this, now it's all in terms of x's, so I'm more comfortable, I'm more relaxed. This is where sort of my comfort zone. So in this case, I'm going to just factor it a little bit, or FOIL it a little bit, distribute a little bit, so that it's easier to take the derivative. So it's going to be x squared plus 4x plus 2. So now it's derivative time. We change the constraint, the function that we care about, using the constraint in terms of only one variable. So the second step is take a derivative. Looks like my derivative is just going to be 2x plus 4 using the power rule, taking the 2 down, obviously subtracting 1. So then you draw a sign chart of this nice derivative. And again, the sign chart will be pretty easy because you can only employ the first derivative test for absolute maximum min only in certain cases when the sign chart is this easy. So where does this sign chart cross? Well, it's going to be -2. There's only two types of lines in the world, and this is a line, mx plus b. Keeping in mind that it's a positive slope line or a negative slope line based off the slope, not based off the 0. So because the slope here is 2, mx plus b, it's going to be a positive slope line. So it looks like it's going to be from negative to positive. Now we have the sign chart that we want, so now we're going to justify. So f has an abs min at this number. I have to tell the world why I know this is an absolute max or min. It's because f prime goes from is negative for x smaller than this number, 2, and f prime is bigger for x bigger than 2. So f prime is negative, so that means we're just running downhill until we hit 2, and then we run uphill after we hit 2, so that 2 was the absolute min. So you do have to justify though, unfortunately. So that's all the brunt of the work really. So now we're ready for the answer. So again, the minimum occurs when x is equal to 2. We can quickly plug this into the function to find y, because we want to find the actual absolute min of the actual function itself. When you plug in 2, it looks like you're going to get 5. So the minimum value, which potentially is the question, is going to be 2 times 2, 2 squared, which is 4. 4 plus 5 times 2 is 10. So it looks like that minimum is going to be 14. But this is the optimization practice that we're going to practice several more examples of. But what you do is you start off with two functions. You use the function that you know about, the constraint function, to influence the function you care about, the thing you're taking the max or min of, by changing that function in terms of one variable. So in this case, we have x squared plus 2y, and what we did is we plugged in 2x plus 1, so that it's all one variable. Then what you do is you take the derivative, you draw the sign chart of the derivative. The derivative should be pretty simple, so its sign chart should be pretty simple, and then you justify using a sentence. You do have to justify. F has an abs min because f prime is negative for this side of the sign chart, f prime is positive for this side of the sign chart. Finally, once you know your minimum value where it occurs, you just plug in things to find the other values you need. For example, plugging in 2 to find the y, plugging in 2 and 5 to find the minimum. So that's how it works. Now let's do sort of a more mathy word problem questions, because oftentimes optimization are these word problem questions. So what we're going to do is we are going to find, let's write this down. We are going to find two numbers whose difference is 100. I can write the word 100. Whose maximum or whose product is minimum. So this is the power of optimization, and it allows us to answer some of these questions. So basically what happens is we have two numbers whose difference is 100. So there's a lot of pairs of numbers. For example, 150 minus 50, that's 100. But so is the same thing as 110 minus 10, that's also 100. So there's a lot of possibilities. There's actually an infinite number of possibilities. And what we want to do is we want to pair them up and see, multiply them together and see which pair will have the smallest value when you multiply them. Whose product is the minimum. And of course, we can't find an infinite number of things and start multiplying them because that would take a lot of time. So that's why we use optimization. So keep in mind that everything is in English in this case, but it's the same sort of thing. Once we start to convert everything to math, it'll be the same process as the previous question. So what's the constraint here? Well, the constraint is what we know about the question. So I'm going to call my variables x and y because usually students use x and y as their variables. So we have two numbers, x and y, whose difference is 100. So all I'm going to do is write a simple equation. Looks like it's going to be x minus y is equal to 100. Then what we do is we see what we need to find the max or minimum. So it's the minimum. We can call it P for product. And it's going to be x times y. Because again, we're trying to maximize or minimize x times y, the product of the two numbers. So in this case, again, we have two variables, but we don't panic because we can use the constraint to make this one variable. So I'm going to convert to y's because people like to have y's in terms of x's. So it looks like y is equal to x minus 100 because we bring the y over, subtract 100. So it looks like when I substitute in this into our function to make it one variable, I'm going to have x times x minus 100, which is the same thing as x squared minus 100x. So now I'm ready to sort of go for the second step. Notice that I used the constraint how I needed to do it because the function I care about is now only in terms of one variable, so I know how to take its derivative. So the derivative step, p prime of x, that's going to be 2x minus 100. So it looks like x is going to be 50 because 50 times 2 is 100. So I'm going to draw a sign chart. Again, you have to sort of have a nice, easy sign chart. This is going to be negative to positive because we have a positive slope line, and you have to justify, unfortunately. But the justification is the same thing every time. So hopefully as you write these questions out, you'll get used to justifying and you'll get used to the sentence. But P has an abs min at this number, x is equal to 50. And again, it's because P prime, this is a sign chart of P prime, goes from negative to positive, and that's all it does. A better way to say it is P prime is negative for x smaller than 50. P prime is greater than 0 for x bigger than 50. So P prime is negative for x smaller than 50. P prime is positive for x bigger than 50. Once you have the x, it will be pretty easy to find the y. If x is equal to 50, well then remember that y is equal to 50 minus x, or x minus 100, sorry, where x is 50. So it's going to be 50 minus 100. So y is equal to negative 50. What's going to be the product? Well, it's going to be 50 times negative 50. That's going to be the minimum, negative 2500. So again, all we're doing is we're doing the same process. We sort of got a nice result here. Anytime you have the difference of two numbers, if you multiply them together, you will not get a smaller number than negative 250 if their difference is 100. But it's the same process as our previous question. We have a constraint. We use the constraint to change the function we care about to be in terms of one variable. We take the derivative, then we draw the sign chart, we justify, then we answer the question. So let's do some harder ones where the sign chart's a little bit trickier, but in the end, it won't actually be trickier. So let's do a harder derivative, basically. So I'm going to erase this. And what we're going to do is we're going to find the two numbers. Let's see, what do we want? Find two positive numbers. So the word positive is going to be very key in this case. But we're going to find two positive numbers whose product is 100 and whose sum is minimum. So looks like we have sort of the same scenario here. We have some sort of sense, that's going to be the constraint, and then we want to minimize or maximize a different thing. So I'm going to use S for sum. What are we trying to minimize in this case? Well, we're trying to minimize the sum. I'm going to use x's and y's just like normal. So it looks like it's going to be x plus y, where x and y are my two numbers. Keeping in mind that x and y both have to be positive. Again, that's a key part of the question. Then we need to use our constraint. So I'm going to write the constraint right here because I sort of ran out of space. Actually, let's write x of x is equal to x plus y, and we'll write the constraint where it's supposed to go. So what's my constraint? Well, my constraint is that I know that the product of these two numbers is 100. So x times y is equal to 100. What I should do though, of course, is I should bring over the x because I need to change using this constraint function. I want to change the sum function to be only in terms of one variable. So what I'm going to do is I'm going to write 1 is equal to 100 over x. And I'm going to replace the y with this so that I can accomplish my goal. Everything is in terms of one variable, x plus 100 over x. The next step is take the derivative, but if I foresee the future, this derivative might be a little bit annoying. I definitely don't want to do the quotient rule because we don't have x's in both the numerator and the denominator. A lot easier way to take this derivative is to use the power rule with a negative exponent. So that's what I'm going to do. I'm going to change this to be x plus 100 x to the negative 1. So now I'm ready to take the derivative. Let's take the derivative together. So it's going to be s prime of x. The derivative of x is just so nice. It's just the number 1. And then this is why I changed this to a negative exponent so I can take this derivative a little bit more easily. You have the negative 1, you drop it to the front. So it's going to be negative 100. And of course, you subtract 1, negative 1 minus 1 is negative 2. So you have x negative 2. The general rule of thumb is that you change functions to take in terms of negative exponents or fractional exponents if you have square roots or cubed roots, when you want to take the derivative or when you want to take the integral. But what you should do is you change them back if you need to maneuver everything around. Remember that I do need to draw a sign chart, and in order to draw the sign chart, I need to factor everything as much as possible. So in this case, I need to do a few algebra steps before I draw the sign chart. Keeping in mind that x to the minus 2, again, means that it's 100 over x squared. To draw the sign chart of something, everything needs to be as simplified as possible. So what I need to do is I need to take these fractions and smash them together using a common denominator. Looks like it's going to be x squared over x squared minus 100 over x squared. I'm going to keep going. Well, I have a common denominator, so that's going to be x squared minus 100. But x squared minus 100 is x plus 10 times x minus 10. So that looks like my final factored form. It's a difference of squares in the numerator. So this is a good review of sign charts. Keep in mind that sometimes students are intimidated by sign charts when they're fractions, but I would say don't be. All you have to do is just consider this as a regular sort of function. Count your zeros, do your zero behavior just like normal. Watch our sign chart video if you need help with this. But basically, we're going to have this little sign chart. We're going to include every single zero we see, negative 10, 10, and 0. We're going to place them in order, of course. Because we're drawing a sign chart and not a graph, we don't have to worry about how tall things are and things like that. So what I do is, when I have a fraction, I just consider it the same way. So I first answer n behavior. Does this look like a cubic function or a negative cubic function? Does this look like a parabola or a negative parabola on the ends of the function? So it looks like we need to count the zeros, 1, 0, 2, 0, but because this is squared, the multiplicity of the bottom is 2, so it looks like we have 4 zeros from 3 factors. So because we have 4 zeros, we're dealing with something even. Everything is positive because there's no number in the front, so we're dealing with an even positive thing. That's a parabola that starts at the beginning, at the top, and then ends at the top as well. So it's going to start at the top, end at the top. Then you consider the zeros based off the exponent of the corresponding factor. So when I go towards negative 10, I'm asking myself, does this cross or does this go through? Well, because this is to the 1, it's going to go through. Then when I hit 0, because this is to the 2, which is an even number, it'll bounce nicely, bounce. Finally, when it goes through 10, because again, this is to the 1, it'll go through. It looks like I'm ready for my sign chart, positive, negative, negative, positive. So now I need to justify that whatever number I care about is an absolute min. But if you remember from the beginning of the video, the sign chart has to be simple enough where it's either just negative to just positive or just positive to just negative. But in this case, it looks like we have a very complicated sign chart, positive, negative, negative, positive. So this is where the word positive comes in from the very beginning. So what's going to happen is that I can ignore this sign chart because I don't want any negative values in my answers because all the numbers have to be positive. So notice that if I ignore all the negative signs, negative numbers in this sign chart, I have the sign chart I want. It only is negative and then it becomes positive. And that's the situation that allows me to write the following sentence. The sentence being the same sentence as the previous two questions. S has an abs min at x is equal to 10 because S is negative for the sign part of the sign chart you care about. That's from 0 to 10 for 0x to 10, and S prime is bigger for x bigger than 10. Again, justifying this sign chart to make sure that I know why there's an absolute max there. It's because of this sentence right here. It only is negative, and then the derivative is only positive, so it has to be an absolute min at that point. Once you have these x value, it's pretty easy. You just plug in. Notice that when x is equal to 10, y is also 10. So it looks like we're ready for the answer. X is 10, y is 10. Then when we plug it into this function, well, 10 plus 10 is 20, so s is equal to 10 plus 10, which is 20. So again, not the worst thing in the world, same sort of process. Here the derivative was slightly harder, which made the sign chart a little bit harder, but because we could ignore half of the sign chart because we were only dealing with positive numbers, we were good to go. Same sort of thing as the previous ones. Negative to positive, that's an absolute min. A better way to say this again is negative for the first half of the sign chart, positive for the second half of the sign chart. Keep in mind that in optimization questions, because you're optimizing things and the world is sort of constructed the way it is, a lot of times when you're optimizing things, you're going to have things to be symmetrical. So it makes sense that our x value and our y value is the same here. But it's the same process as normal. Use your constraint function to change the thing you care about as a min or max into one variable. Take the derivative. If you need to take the derivative with power rule, just take the derivative with power rule. Simplify the derivative as much as possible. Draw a sign chart of it. Write the nice little sentence once you ignore the sign chart half that you can, and then finally answer the question. So let's do a few more questions. Let's do questions that involve geometry. So let me erase this. So what we're going to do is we're going to find the dimensions of a rectangle, because we want to do geometry. Who's with perimeter 10. Well, let's do 100, just like normal. Whose area is as big as possible. If I can spell the word area. So you do need to know English when you do these questions. Big as possible, of course, means absolute max. So this is our first absolute max question out of the first 4 questions. Keep in mind that if you're doing these optimization questions, it will magically work out. When you have the absolute min, you'll have a nice min sign chart. When you have an absolute max, you'll have a nice max sign chart, positive to negative. So let's see how this works. So first off, let's try to locate the constraint function and also the area, the thing we're taking the max or min of, which is the area function. So when you have a rectangle, I'm going to call this x, x, y, y. Well, what's the perimeter? It's going to be 2x plus 2y equals the number. So perimeter is equal to 2x plus 2y is equal to the current number that we know, which is 100. So this is what is going to be the constraint function, because this will allow us to change the area function to be in terms of one variable. If you want, you can already sort of simplify this. X plus y is equal to 50. Y is equal to, if I can write a 50 actually, y is equal to 50 minus x. I know I'm going to use this eventually, so might as well find it. So the thing I care about actually is the area. We're going to call that A for area. And what are we trying to maximize? Well, we're trying to maximize the area. The area of a rectangle is base times height, or length times width. In this case, x times y. So it's going to be x times y. I start panicking just a little bit because x times y is 2 variables, but I don't panic too long because I remember I can plug in that 50 minus x into our function. So it should be x times 50 minus x. If you want, you can sort of distribute it, because if you didn't and you took the derivative now, you would have to do product rule. So let's do 50x minus x squared. So now we're ready to take the derivative, a prime of x. The derivative here is going to be the power rule again, 50 minus 2x. So it looks like it's going to cross at 25. And now we have our first negative slope line, because it's, I can't write the word 25. Looks like we have our first negative slope line because it's mx plus b, where m is negative 2. And again, if you're doing the question correctly, it'll magically work. We're doing a maximum question, so that's why we have a maximum sign chart, positive to negative. Let's quickly justify. So the justification is the opposite of the previous ones, because we have an absolute max. So A has an abs max at this number right here, 25, because A prime is positive, just describing the sign chart, positive for the first half, negative for the second half. And A prime is negative for x smaller than 25. Finally, we do want to answer the question. So if x is equal to 25, what is y? Well, y is equal to 50 minus x, so y is 25 itself. And then what's the area? Well, the area is going to be 25 times 25. That's 5 hypercubed, I guess, 5 to the 4th. So that's going to be 625. Like we talked about in the previous question, oftentimes these optimization questions are symmetrical. So it makes sense that to maximize the area of a rectangle given a limited perimeter, what you want to form is you want to form a square. That's going to give you the maximum area. That makes sense. So let's do one more question that's really similar to this. involving a nice little farmer. Don't know the name of the farmer, but we'll just call him Farmer and we'll be good to go. So one more question just to get the hang of this, and we should sort of be somewhat familiar with how to do these questions. Constraint function into the other function, take the derivative, draw a sign chart, justify, write the answer. So in this case, we are going to be finding, we have a nice little farmer man or woman, I don't know. Whoever this is has 100 feet of fencing. So it's going to be similar to the previous question where we had 100 units of the perimeter. And he's trying to build some sort of fence. So he's trying to build a fence. But the thing about it is he's building a rectangular fence or a field or something. Fence. Let's say a fence surrounding a rectangular field. Let's actually use English. Surrounding a rectangular field. So once we have this fence, the key is that he's building it along a river. So this is my nice little picture of a river. Hopefully you can tell that this is a river, it's labeled. But the key is that along the river, he doesn't need any fence. So along the river, no fence required. So the question is, of course, what are the dimensions of the fence to make the field's area as big as possible? So what are the field's dimensions? To make the area as big as possible for a largest area, we'll just say. So hopefully I have enough room because the question took up more than half of the board, but it's the same thing as normal. You have some sort of constraint. You're trying to find maximum or minimum with something else. So we're going to use that constraint to make this function one variable, then we'll take the derivative. So let's do that process. So it looks like my constraint, so we can call it constraint. Well, it's going to be, let's label this x and y. So unlike the previous question, it's not going to be 2x plus 2y is 100 because I don't need fence along this side right here. So it's going to be x plus 2y is 100. So x plus 2y is equal to 100. That means that y is going to be 100 minus x divided by 2. So that's going to be the thing I'm going to plug in. So let's write that thing I want to take the maximum of. It's going to be a of x, of course. So what is the area? It's going to be x times y, just like the previous example. We're trying to maximize area, and that's the area of a rectangle. It's going to be x times this because this allows me to change these two variables into one variable. X times 100 minus x over 2. We can distribute this a little bit. So it's going to be 50x minus x squared over 2. Then we're going to take a derivative. So a prime of x is equal to, well, the derivative here, it should be 50x, of course, because it's x times 100 divided by 2. The derivative is going to be very nice. It's going to be 50x. Then to take the derivative of this, certainly do not do quotient rule. Think of this as 1/2 times x squared. So you take the 2, drop it to the front one last time. The 2 and the 1/2 will actually cancel each other out. So you're just left with minus x. So 50 minus x. Of course, the derivative of 50x is just 50. I don't know why I wrote 50 minus x. So in this case, what's going to be the, are we doing this right? I don't know if we're doing this right. What are we doing wrong? What are we doing wrong? So 2x, x plus 2y is 100. So then 100 minus x over 2. Then we're squaring everything. We're taking the derivative. X squared over 2, 2x. X is equal to 50. Oh yeah, all this is right. I don't know why I'm confused. So x is equal to 50. So we're going to draw our nice little sign chart. 50. Then we're going to have a negative slope line. So it's going to look like this. It's going to go positive and then negative. We do have to justify. So let's justify one last time, just one last time. A has an abs min, or max, because we're trying to find max, because it goes positive and negative, at this number right here. One last time, it's because the derivative is positive for x smaller than the number, the derivative is negative for x bigger than the number. So because A prime is positive for x smaller than the number, and A prime is negative for x bigger than the number. This makes, if we can write the answer right here, this makes the x 50. This justifies that the minimum does, or the maximum does occur at this number 50. What is y? Well, y is going to be 100 minus 50 divided by 2. That's going to be 25. Still pretty symmetrical. Finally, what's going to be the dimensions? It's going to be 50 times 25. 50 times 25 doesn't seem too bad. I think it's going to be 1250. So the area is 1250. I don't know why I got flustered there in the middle of this, but hopefully you see that this process was the same thing every single time, even if you have these word problems that often appear on college calculus exams. So what you do is you take your constraint function, which you have to convert from English into math, then you use that constraint function through substitution to change the function you care about, the thing you're taking the absolute maximum in, into one variable. So in this case, we plugged in 100 minus x over 2 into this. We sort of distributed, and then we took the derivative, not using the quotient rule, but using power rule instead. We got the number x is equal to 50 eventually. Don't know why I stumbled there, but we got x equal 50 eventually. We drew the sign chart. You do have to justify. Please remember the justification sentence. It's just something that you can just see as you look at it. All you're doing is describing the sign chart. A prime is positive for x smaller than the number. A prime is negative for x bigger than the number. This is a little 50 if you can't tell in the corner. Finally, if x is equal to 50, we can plug back into the constraint to find y, that's 25. And finally, we can plug it into the function, 50 times 25, 1250. So for our nice farmer friend, we know exactly what the biggest fence, the biggest field that farmer can potentially make, and it's going to be 1250. So hopefully this video has been useful for you. We did talk about two main things, the optimization and the alternative way to do absolute maximum in order to justify that the answers we get in the optimization question are indeed the maximum or minimum. But again, it's the same thing every single time. Constraint function, change the constraint function to, or use the constraint function to change the function you care about to be in terms of one variable. Take the derivative slowly, draw the sign chart. It has to be either this line or this line right here. If you ignore parts of the sign chart that are able to be ignored, then justify using that alternative way. The alternative way being the derivative is negative for x smaller than the number, and the derivative is positive for x bigger than the number for an absolute min, and the absolute max is reverse. But optimization is certainly a hard concept, so if you want more practice examples that are very similar to these, and maybe some harder ones that involve 3D shapes instead of just 2D shapes, what I would do is suggest watching our video, our Girls Teach Calculus video, that I'll link in the description below, where one of my former students practices several of these examples. She goes over the absolute max or min process again. She talked about the optimization process that I talked about quite frequently throughout this video. So be on the lookout for that. Check out that video if you want more practice. But thanks again for watching this video. Hopefully it was useful for you. You know how to do optimization. Continue watching this video series if you want to keep sort of exploring harder advanced derivative topics that might appear on the AP exam. But no matter what, thanks again for watching. Just like normal, like and subscribe if this video was useful for you, and I hope to see you next time, whenever that is. Thanks again.